Good day, grade 11s. Welcome to today's edition of Learn Extra. We're going to focus on revising chemical reactions. Now, when we work with chemical reactions, there are two types of reactions that we work with in grade 11. The first type of reaction is known as a redox reaction. When we deal with redox reactions, we look at the transfer of negative particles, also known as electrons. The second type of reaction we're going to look at today is an acid-base reaction. Now, when we work with acid-base reactions, we look at the transfer of positive particles or protons. And in this case, that proton is going to be the hydrogen that is donated or accepted. But let's start off with a quick revision on redox reactions. The key concepts that we need to look at over here would be the redox reactions that we start off with. Remember, as I said, when we work with a redox reaction, we are going to look at the transfer of electrons. There are two types of redox transfers, the ones where we work with direct transfer of electrons and the ones where there are indirect transfer of electrons. Now, direct transfer of electrons would refer to your spontaneous redox reactions. That would be the primary focus of our studies for this year. We also have non-spontaneous reactions. And when we deal with non-spontaneous reactions, we are going to look at an electrical transfer whereby electrical energy is converted into chemical energy. A lot of our focus will be on doing that next year when we work with grade 12 chemistry. If we move on, we will see that we are going to look at assigning oxidation numbers. Now, the rules for oxidation numbers are very important for us to help us to determine where the electron transfer has taken place. And then lastly, we're going to have a quick look at the table of standard electrode potentials. This is very important because it becomes a valuable tool that helps us in working with redox reactions and also in working with half reactions, which we will look at a little bit later. During a redox reaction, we are actually working with two types of reactions. The first one is known as an oxidation reaction. During an oxidation reaction, we encounter a loss of electrons. There are various acronyms that we can use to help us to remember that oxidation refers to the loss of electrons. We will get to those a little bit later. The second type of reaction is a reduction reaction. Now, a reduction reaction refers to the gain of electrons. Remember, I've mentioned the acronyms that we have. Two of those would be as such. The first one is the one where we say that Leo says Gur. Now, we are going to focus on the Leo and the Gur part. If you look over here, the loss of electrons is oxidation. That is where the Leo comes from. Alternatively, if we look at the gain of electrons, which is your reduction half reaction, that is where the Gur comes from. So we try and make a sentence that will help us. And then we say Leo says Gur, remembering that loss of electrons is oxidized, the gaining of electrons is reduced. It might just so happen that your teacher has told you about an oil rig. Now, if you go and look over here, oxidation is the loss of electrons. So we're using the oil to remember that we have oxidation, and reducing is the gain of electrons, whereby the rig would refer to your reduction half reaction. Whichever acronym you decide to use because you are familiar with it or it seems easy to remember, remember that it is only a tool to help you remember. You cannot go in an exam or in a test go and write Leo or Gur or oil or rig as an answer. You need to still give us the proper explanation that oxidation is loss of electrons, reduction is the gaining of electrons. As I said, the acronym is only there to help you remember that information. If we move along, we will see over here that the redox reaction is actually both of those reactions taking place at the same time. And that is why we call it a redox. We are using the red as part of your reduction that we refer to, and the ox for your oxidation reaction. So that is where the name comes from. In some redox reactions, we find a spontaneous transfer of electrons. These are called spontaneous redox reactions. When such a reaction takes place, the moment the chemicals are joined together, the reaction will take place on its own. No energy needs to be added into the system. When we deal with other reactions where we have an indirect transfer of electrons, those reactions are also referred to as non-spontaneous reactions. Because we need to transfer electrons into the system, because the electrons are not provided by the chemicals themselves, we use electrical energy to provide the necessary electrons. Such redox reactions are also referred to as electroplating reactions, whereby metals are extracted from such a reaction. A lot of emphasis comes into this section next year when we do this in matric again. If we look at the direct transfer of electrons, we look at the following example. If you have a reaction where you have a zinc rod that is placed into a container that has a solution of copper sulfate, you would encounter the following. The copper sulfate solution over here would have a blue color. Remember that zinc over here is a metal, and that it would actually in fact have a silver color. It is the copper sulfate solution that has the blue color. If I allow the reaction to take place for a significant period of time, I will notice that the blue color disappears out of my solution and it becomes colorless. While this is happening, I will also find that there will be a red-brown residue forming in the solution all around the piece of zinc that I had in there. Now this red-brown color is actually copper that has been taken out of the solution. So if we go and we look at the chemical equation that we have here, we will notice that the zinc has gone from an atom which has got a 0 charge into an ion that is now part of a bond. The copper, on the other hand, has gone from a solution where it was part of a bond into an atom that is now on its own. Now, for that process to take place, there needs to be a transfer of electrons. So we go and we look at the transfer that takes place based on the chemical reaction. If you go and you look at the reaction, we start off with zinc as a neutral atom. Here we have already gone and taken the copper sulfate and broken it up into the ionic form. You have your copper ions and your sulfate ions. Then we move over to the product side. Here we now notice that the zinc has gone into an ionic form and the sulfate is also in an ionic form. And now we see over here that the copper is an atom. Just make sure that your notes indicate over here that this 4 is a footnote, and that 4 is also a footnote in your notes over there. Now, when you look at this, you will notice that zinc has gone from a neutral atom to an ion. It has gone from 0 to +2. Now, for something to become more positive, something negative has to be lost. And in this case, that negativity that has been lost is the electrons that were lost by the zinc atoms to form the zinc ions. On the other hand, your copper has gone from a Cu2+ all the way to a copper that has now got a neutral charge. So that transfer that has taken place tells us that to get rid of the extra positive 2 charges, negative electrons were gained, and that gave my copper an overall neutral charge. So you will see the 2 electrons that were lost by the zinc were gained by the copper. No electrons were lost in this entire reaction. They were only transferred from the one substance to another substance. If you go and you look at the half reactions, now a half reaction over here is characterized as a reaction that is only one half of the entire reaction. You will notice that we look at the reaction where zinc is only, or we go and we look at the reaction where we have our copper only. Now your zinc on its own has been the one that has lost its electrons. It has gone from a 0 charge over here to a +2 charge on this side. That tells us that electrons were lost. Remember that the loss of electrons is your oxidation half reaction. On this side, just so that you guys can all see, your copper has gone from a +2 charge, whereby it gained electrons and it turned into copper with a 0 oxidation number. Now, what are these oxidation numbers that I'm talking about? If we go and we look at the elements that we have over here, all of these elements are assigned oxidation numbers, and we can go and look at some basic rules to help us with oxidation numbers. These rules are simplified to 4. They can be as many as 7. We have condensed them into the 4 basic ones that you need to know. All elements have an oxidation number that is equal to 0 when they are unbonded. When I'm talking about an unbonded element, I'm talking about an element in its pure form as it appears on the periodic table. If I have a piece of copper or a chunk of sulfur or a little bit of phosphorus gas, all of those elements are unbonded, and therefore they would carry an oxidation number of 0. So if you go back to the previous equation that we looked at, you would see that zinc over here is unbonded, and therefore it has an oxidation number of 0. Your copper over here is unbonded and therefore carries an oxidation number of 0. The second rule over here tells us that the total oxidation number of a compound is 0. So if I take that into consideration and I look at the following and I tell you that we are working with fluorine gas. Fluorine gas is a diatomic molecule, so it is bonded to itself. This is a neutral compound, and therefore the oxidation number for fluorine gas would be 0. Be very careful not to confuse oxidation numbers with valency numbers. If we look at another compound like copper oxide, CuO, if I go and I look over here, the sum of the 2 oxidation numbers of those elements would have to equal to 0. So therefore, if I go and I look at any compound and it's a neutral compound, then the oxidation number will be 0. If we look at the third rule, it refers to that of a polyatomic ion. Polyatomic ions are also referred to as your compound ions and some textbooks call them your radicals. Now, compound ions or radicals are groups of nonmetals that have combined together to form a compound. But this compound still has unbonded electrons. So these unbonded electrons will cause a charge to be surrounding the entire molecule. Now that charge is going to be the same as the oxidation number for the entire molecule that you work with. Also, when you work with positive compound ions, such as ammonium and hydronium, the oxidation number in this case would carry a positive value. For each of these 2 compounds, that oxidation number is +1. The last rule tells us that in a compound, the unit oxidation number of hydrogen is always going to be +1 and oxygen is always going to be +2. So if I look at these 4 rules and I apply it very quickly over here to 1 or 2 examples, we will notice the following. If we use the example of copper oxide again, now the overall oxidation number must equal to 0. The rule tells me that oxygen has an oxidation number of +2. So if I wanted to go and find the unknown value over here for copper, I could do it in a simple mathematical equation. You make copper over here your unknown. You can make it an X, or you can keep it over here as copper, plus the -2 value for oxygen, and the sum of those two oxidation numbers should give you 0. If you take the 2 across, you will find that the oxidation number for copper is going to be +2. Very, very important over here that you include the operator. So you must include that it is a positive or a negative number. So the oxidation number for copper in this specific compound is going to be +2. If we look at another example, for instance, sulfuric acid, H2SO4. If you look over here, you will notice that we've got hydrogen, which is always assigned the number +1. We also have oxygen, which is always assigned the number -2. This is an overall neutral compound, so the oxidation numbers should add up to give me 0. If I go and do the calculation to go and find the oxidation number for sulfur, I would do it as such. I have 2 hydrogens, which each carries an oxidation number of +1. Let's just separate those two calculations. My sulfur is unknown, and I have got 4 oxygen atoms, which each carry an oxidation number of -2. Now, all of these oxidation numbers need to add up to a total of 0. 2 times +1 is going to give me +2, plus the unknown value for my sulfur, plus 4 times -2 is going to be -8. You would see that I like to keep things in brackets so that I can, when I move them across, change the operator appropriately. So +2 minus -8, or plus -8, which is going to be -8, is going to give me -6. So sulfur -6 is equal to 0. If I take the 6 across, I will see that my sulfur is therefore going to have an oxidation number of +6. Now, if you wanted to compare that to your valence number, you would see that the valence number for sulfur is +2, or -2, apologies. So you would see that the oxidation number and the valence number have got nothing to do with each other. Let's just have a last example to see how rule number 3 is applied when we work with a compound ion. Let's use the example over here of ammonium. Ammonium is the compound ion NH4, which carries a +1 charge. We generally just write it as NH4+, and over here we see that we've got hydrogen. Now remember that hydrogen has got an oxidation number of +1. So if I go and I look over here, I will see that my nitrogen has an unknown oxidation number. I have got 4 hydrogens, which will then carry a +1 charge each. And the overall oxidation number is going to be equal to the 1 that I have over there. So I write here +1. 4 times +1 is going to be +4. So nitrogen plus 4 is going to be equal to the oxidation number of 1. If I take the 4 across, it's going to become -4, and I see that nitrogen in this case has an oxidation number of -3. So I hope that has given you an idea of how we use those rules to go and calculate the oxidation numbers. The 4 rules were condensed. Let's go over them again quickly. An unbonded element, or an element in its pure form, will have an oxidation number of 0. If I have a compound, the oxidation number for the entire compound is going to be 0, because the oxidation numbers for the elements in the compound should add up to 0. If I have a compound ion or a polyatomic ion, then I will notice that the oxidation number is equal to the charge. That comes from the oxidation number of the different atoms being added together and then adding up to the charge that I have for the compound ion. And the last rule is the easiest to remember. Your hydrogen will always be +1. Oxygen is always -2. And if you can remember this, all of your group 7 elements will have an oxidation number of -1 when they are part of a compound. All right, so let's move on to the next slide. If we go and we look over here, we're going to quickly discuss the table of electrode potentials. Now, in the matric exam, you receive 2 standard tables for your electrode potentials, Table 4A and Table 4B. Please make sure that you know exactly which table to use. Different teachers choose different tables to work with. For the purpose of the work that we're going to do over here, we are going to work with Table 4B. So if you have a copy in front of you, go and have a look. Make sure which one it is that you are going to work with. Now, the standard table gives us an overview of half reactions that we are going to work with. As I said, for the purpose of this example, we're going to work with Table 4B. Table 4B starts off with lithium at the top and is going to end with fluorine at the bottom. Your half reactions are arranged in such a manner that the half reaction with the highest reduction ability is ranked at the top, and the one with the highest oxidation ability is ranked at the bottom. Now, if it has got a higher reduction potential ability or reduction ability, it is going to have a very low oxidation ability. And if it's got a very high oxidation ability, the reduction ability will be very low. Now, that oxidation or reduction ability will make the substance a good reducing or oxidizing agent. Remember that a reducing agent itself undergoes oxidation, and an oxidizing agent undergoes reduction on its own. Also important to remember over here is the E naught value. You will find E naught is written as an E with a 0 at the top when you go and you look for it on your table. Now, the E naught is just an indication of the oxidation or the reduction ability. Next year, we're going to use those E naught values to go and calculate the potential difference or the voltage that is generated by such a cell, whereby we use redox reactions. If you go and you look over here, if it has a positive E naught value, then we know that it is a very strong oxidizing agent. And if it has a negative E naught value, that it is a very strong reducing agent. When we work with a reducing agent, we always read it from right to left. And when we work with an oxidizing agent, we read it from left to right, as we read it in the table. Now, the substances that we find at the bottom left are the ones that are most easily reduced, and they are the best oxidizing agents. Your strongest reducing agents are the ones that we find on the top right-hand side of the table. Again, I'm going to ask that you go back and you look at the specific table that you guys work with at your school. For each one of these tables, your teacher would give you the relevant information regarding oxidizing and reducing agents. Now, when we use the redox table, and we're going to use Table 4B over here, just so that you guys can remember, we're going to just extract a couple of examples over here for us to work with. Now, they tell us we are going to work with the one that has lithium at the top, which is 4B, as I said. And when we read it from right to left, it is going to be an oxidation half reaction. And when we read it from left to right, it is going to be the reduction half reaction. So this is just an extract of what you would find on such a redox table. And you will see, very important over here, here is your E naught, which gives you your potential difference. And you'll see that there's a positive value and some of them have negative values. Also over here on the left-hand side of the table, you will find that you will have your redox reactions written down. But you should notice the double arrow over here. Now, the purpose of the double arrow is to indicate to you that that reaction can be read in a forward direction or in a reverse reaction or direction. If you go and you look over here, the zinc, if I read it from left to right, is going to lose or gain electrons and turn into your zinc with a 0 oxidation number. But if I were to read the same reaction from the right-hand side to the left-hand side, I would read it as zinc that loses 2 electrons to become a zinc ion. If I read it from the left to the right-hand side, I'm going to only use the arrow which indicates the direction that I read it in. If I read it from right to left, I'm only going to use the arrow pointing towards my left. So it is very important that you are absolutely sure of the direction in which you are working with your reaction over here. Now, the reason why we have the zinc and the copper over here, if you go back to the very first example that we did over here, you will remember that we worked with zinc and we worked with copper. So going back to this specific slide where we have the table, if you look at it, you will see that we have the zinc and the copper. Let's just erase this so it looks similar to what we have on the redox table. Now, if given a reaction as you were in the previous slide, let's just write that down so we know what we're talking about. If you remember the example that we had, they told us we had zinc metal that reacted with a copper sulfate solution. This resulted in a zinc sulfate solution and copper metal. Now, the easiest way for you to look at this and to know where to go and find the substance and how to read it is to go back to your potential chart. You will see that over here on your reactant side, you start off with zinc. It is not an ion, it is an unbonded atom. Go and circle the zinc. It will help you to know the direction which you are reading it. The zinc then ends up over here as an ion which is part of a solution or a compound. So you're going to read this reaction from the right-hand side through to the left-hand side. On the other hand, if you go and you look at your copper, copper over here is part of a chemical bond. So you're going to look for copper and you will see very quickly that your sulfate has got a -2 charge. So that means that your copper over here will have an oxidation number of +2. The reason why this is important is you'll find copper with a +1 or a +3 oxidation number on the chart. So we're going to use the copper which has the +2 oxidation number, and we see that the copper goes from an ion all the way through to copper as a neutral unbonded element. So I'm going to read this particular reaction from the left-hand side to the right-hand side. So you're going to use your balanced equation to determine in which direction you're going to read it. So the zinc has gone from a 0 all the way to a +2, and your copper has gone from +2 all the way to 0 oxidation number. Now, if you read it from the right-hand side to the left-hand side, this is going to be your oxidized reaction or your oxidation half reaction. And if you read it from the right-hand side through to the left-hand side, this is going to be your reduction half reaction. Because if I read it from left to right, I see that my copper gains electrons to become reduced, and over here my zinc loses electrons to become oxidized. And from there we can now go back to where we were in that slide with our example, where we will see that you have an oxidation half reaction, and in your oxidation half reaction there we had the zinc. You write only one arrow in the direction in which the reaction is taking place. So I'm reading it from my right-hand side to my left-hand side, and it turns into zinc with a +2 charge, and it liberates or loses 2 electrons. My reduction half reaction would be that where my copper has gone from an oxidation number of +2, it gains 2 electrons, and it turns into copper with a 0 oxidation number. Now from here we need to go and establish a net reaction or an overall balanced equation that tells us where the transfer has taken place and the ions and the atoms that we work with. Now important over here is to go and identify the arrows. You would see that the arrow is situated over here, and the reason why I highlight that is because if I have substances, or in this case electrons, that are at opposite sides of my arrow, I am allowed to cancel them out. So I see that my electron over here is on the right-hand side and over here on the left-hand side of the arrow, and I can go and cancel those two out. Make sure that you cancel the right number of electrons out, because in the net equation, we do not write any electrons. We tend to write, or I tend to write the unbonded elements first. So I start off with my zinc, and I then have my copper 2+, and over here it will form my copper and my zinc with a 2+, not a 2 with a zinc plus. So there's your zinc, and it's got a 2+ oxidation number, and that is then your overall net equation. Just a quick reminder, if it does happen that you write your oxidation and your reduction half reactions, and you notice that you've got 1 electron and maybe 3 electrons, you balance the oxidation reduction half reactions by multiplying it with a common multiple. So in that case, I would use the equation that has got 1 electron and multiply it by 3 so that I can cancel my electrons out evenly. At the end of the day, in your net reaction, you should not have any electrons written down at all. All right, just a very quick recap on the second type of chemical reaction. The second type of chemical reaction over here is known as your acid-base reaction. An acid-base reaction is the reaction where we look at the transfer of protons. Now, we teach you when we deal with electricity that only electrons can move around and there are no protons to move around. But if we go and we look at the element hydrogen, hydrogen consists of a proton, and around the proton in an orbital we find a single electron. If I were to then go and remove that electron to form hydrogen ion, that hydrogen ion consists of the proton only. So when I'm talking about a proton that is transferred, I am actually referring to the hydrogen ion that is going to move around between two substances. By definition, and this is a Brunstad-Lowry definition, these were two scientists that did a lot of work and research on acids and bases. They gave the definition of an acid and base as the following. An acid is known as a proton donor. And when I'm talking of a proton donor, we know that someone that is a donor donates or gives something away. So an acid is going to give away a proton. They will give away their hydrogens. So if you look over here at very simple one, sulfuric acid, your sulfuric acid will release over here hydrogens. And there's your hydrogen ion, and you'll see that there's 2 over here, so I'm going to have 2 hydrogen ions. Then I will also have my sulfate ion, which is now going to become a spectator ion. We call it a spectator ion because it does not take part in the reaction itself. Now, if my acid is a proton donor, what would my base be? Now, according to Brunstad and Lowry, a base is known as a proton acceptor. So they are the ones that would accept the protons that are given off by the acids. So if I look over here at, let's look at ammonia, which is NH3. If it were to accept a proton over here, it would turn into ammonium, which is also a rather strong base that we work with. So that is the basic definition that we have for acids and bases, that an acid would be a proton donor. They would give away their hydrogens, which are the proton carriers, and a base is a proton acceptor, and it would therefore take on the proton and increase the number of hydrogens that it has in the bond. Right, from there, let's quickly go and look at a couple of examples and questions that we have provided for you. From the example questions, we'll look at question 1. They tell us that a piece of magnesium ribbon is reacted with hydrochloric acid. So over here, immediately we see we've got a magnesium and we've got HCl. They want us to complete the following reaction. They tell us that we've got magnesium reacting with the HCl. Now, a very simple thing occurs over here. The magnesium is unbonded. If I look at my HCl, hydrochloric acid, I know that this is going to become a proton donor. So what happens is that your HCl, your hydrochloric acid, is going to break up into a hydrogen ion and a chlorine ion. Magnesium, on the other hand, is a metal, and all metals will form positive ions. So when I have this reaction taking place, it will form a salt and it will liberate hydrogen. So if it's going to liberate hydrogen, it means that somewhere over here, hydrogen is going to form, and it forms hydrogen gas, which is always written down as H2, which is a diatomic molecule. Now, if hydrogen is no longer part of my reactants anymore, it is now already in the product phase, that means that I only have magnesium and chlorine left. If magnesium and chlorine were to combine, they would form a metal salt known as magnesium chloride. If you want to, you can refer back to your periodic table where you will see that magnesium is going to lose 2 electrons to turn into your magnesium 2+ over there. So because it carries that positive 2 charge, when it reacts with the chlorine, which carries a -1 charge, we will see that it forms the ionic bond, which is MgCl, and the 2 that I had over there settles at the bottom, because this magnesium has got 2 bonding arms and chlorine only has 1, which means that I can attach a chlorine over here and I can attach a chlorine over there to go and form the bond. So when they ask me to go and complete the reaction, I can rewrite the entire reaction as such. Remember that for grade 11, we expect you to be able to write balanced equations already. So you're going to have magnesium that is going to react with your hydrochloric acid. This will form magnesium chloride, which is your metal salt, and it is going to liberate hydrogen gas. Now remember, this is going to be in a solution, this is going to be a gas, there we have a solid, and this was also in an aqueous solution. If we go and we balance it, you will see that there I have 2 hydrogens and I have 2 chlorines, while on my reactant side I only have 1 hydrogen and 1 chlorine. So I would bring the 2 in front to balance my hydrogens and my chlorines. I only have 1 magnesium, so for that part of the equation it is already balanced. Let's look at 1.2. 1.2 asks us to write the oxidation half reaction for this specific reaction that has taken place. For us to know that, we need to go back and think about which element over here lost its electrons. That's right, if you remember the previous slide, I spoke about the magnesium that loses the electrons to go and become a positive ion over there. So if we go and we look at the oxidation half reaction, we would see that the magnesium goes from being a solid metal that is unbonded to magnesium, which carries an oxidation number of 2+, because it has lost 2 electrons. So there we go, your oxidation half reaction. What I want you to please pay attention to over here is that you only write a single arrow and it points in the direction which your reaction is going to take place. Question 1.3 asks us to write down the reduction half reaction. Now in this case, we would see that the hydrogen was the one that went from a charged to something that was not charged. Remember, when hydrogen is that unbonded or diatomic molecule that it is over here, it carries an oxidation number of 0. That means if I have 2 hydrogens, I had 2 hydrogens over here, and these ones gained electrons. Now for each hydrogen that gains an electron, I am going to have to balance it, and my reaction took place in that direction. So you would see over here a gaining of electrons took place. It went from a +1 to a neutral or a 0 oxidation number over there. And that is your half reaction. Question 1.4 asks us to name the spectator ion. The spectator ion, as I mentioned, is the ion that does not take part in the reaction at all. And if I give you the reaction again very quickly. We started off with HCl that reacted with the magnesium, and that gave us magnesium chloride, and we had hydrogen gas over here. Now we noticed that hydrogen went from being a +1 to a 0. Magnesium went from a 0 to a +2. Chlorine, on the other hand, has remained with a -1 oxidation number throughout. So your chlorine did not take part in any of this at all. So in this case, where they ask us for the spectator ion, your spectator ion would be the chlorine ion over here. Alternatively, you could have written over here the Cl -1, and that is also correct. Question 1.5, they want us to name the reducing agent. Remember right in the beginning when I started talking about oxidizing agents and reducing agents, I said that the reducing agent would be the one that undergoes oxidation itself. So if I go and I look at the two elements that I had, which one underwent oxidation? Of course, the one that I find in my oxidation half reaction. So my reducing agent in this case would be my magnesium ion over here, or the magnesium as it is over there. And if magnesium is my reducing agent, then automatically my hydrogen would be my oxidizing agent. And we see over here that that is exactly what they ask us in 1.6. Your oxidizing agent, in this case, would be the one that undergoes reduction, and that would have been your hydrogen over here. All right. Straightforward questions, not that difficult, not that intricate. In question 2, we're going to look at how can we use oxidation numbers to determine whether a reaction is an oxidation-reduction reaction or not. Question 2. They ask us to use oxidation numbers to identify which of these are redox reactions in each of these reactions. So if you go and you look over here, you will see that they give us 3 reactions. Each of these reactions deal with sulfur and oxygen, and in the last one there's a hydrogen involved as well. The best thing to do is to go and, for me, just to create space, and then I'm going to rewrite these so that we can see which ones are oxidation reactions. We start off with sulfur and oxygen, and it is going to form sulfur dioxide. Now, over here, the sulfur is unbonded, which means that my sulfur will have an oxidation number of 0. So if we have our oxygen over here, which is a diatomic molecule, we will notice that the oxygen has an oxidation number of 0. If we move over to our product side, we see that we've got a compound over here. Remember the third rule that told us that if we have a compound, the sum of the oxidation numbers should equal to 0. So let's see what those oxidation numbers add up to. I have got 2 oxygens, and we know from our rules that oxygen always carries an oxidation number of -2. That means that my sulfur has got to have an oxidation number that will balance out the -4 that I have over here because of the oxygen, because it should add up to 0, which means that my sulfur is going to have an oxidation number of 4. So what we see in this case, and that is a +4, what we see in this case is that my sulfur has gone from a 0 through to a +4 oxidation number. My oxygen, on the other hand, has gone from a 0 all the way to a -2. So the one has gained electrons and the other one has lost electrons. If it has gained a negative oxidation number, it means that electrons were gained. So this one gained electrons, and therefore it was reduced. My sulfur was the one that lost electrons and was therefore oxidized. So over here you will see that my acronym is coming into place. I see that loss of electrons is oxidized for Leo, the gaining of electrons is reduced. So we were able to identify this as an oxidation reduction reaction because of the transfer of electrons. They ask us where we find a redox reaction to go and identify the reducing agent. Now remember, the reducing agent is the one that undergoes oxidation. Which one underwent oxidation in this case? Well, the sulfur is the one that lost electrons. So for this specific one, for this reaction over here, your sulfur was your reduction or reducing agent. So sulfur is your reducing agent. You will see that I use the abbreviation over there for reduction as red. I'm running out of space. In the exam, we would expect you to write it out in full. If we look at the next reaction over here, there we start off with sulfur dioxide, which reacts with oxygen to form sulfur trioxide. Just for interest, these reactions over here form part of what we call the contact process. Next year in grade 12, you are going to deal with this again. It's part of a chemical system whereby sulfuric acid is produced. So these form part of the steps in the contact process to produce sulfuric acid. All right, we're going to use this equation where we have sulfur dioxide that reacts with oxygen. So we have SO2 that is going to react with O2, which is your oxygen, to form sulfur trioxide. We're going to just go and use the balancing that they have over there. We balance it by bringing in a 2 on each side, and we're going to use this equation. From the previous equation, we're just cheating a little bit over here because the information is at hand. You will see for sulfur dioxide, the oxidation number for sulfur over here is 4, which I'm just bringing over from over there. Your oxygen will always have an oxidation number of -2. The oxygen that I have as the oxygen gas over here has an oxidation number of 0. If I go into this my product side, I will see that oxygen still has a -2 oxidation number. Let's write that again. So it still has a -2 oxidation number, but now I need to go and calculate a new oxidation number over here for my sulfur. Remember, that 3 goes in front of my 2 over here, and the sum of my oxidation numbers should add up to 0. 3 times -2 is -6, and for that to become 0, I need to add +6 on this side. So if we have a quick look over here, we will notice that my sulfur has now gone from a +4 to a +6, which means it has lost 2 more electrons. So further oxidation has taken place over there. My oxygen, this one has remained at -2, but this oxygen has gone from 0 all the way to -2. So that one has undergone your reduction. So gaining of electrons, reduction has occurred. Over here we have the loss of electrons and oxidation has occurred. Remember that the one that undergoes oxidation is going to be your reducing agent. So to answer the question where they want us to identify the reducing agent, it is going to be my sulfur yet again. So sulfur is going to be, for equation B, my reducing agent. We're going to start over here with the sulfur trioxide to do our last reaction. You'll see that the sulfur trioxide reacts with sulfuric acid to form H2S2O7. Again, they want us to go and find out whether this is a redox reaction, and if it is a redox reaction, they want us to go and identify the reducing agent. So we have our SO3, which reacts with the sulfuric acid, H2SO4, and that is going to form our H2S2O7 over here. And just to make sure about the balancing, we will see that there's a 2 in front over here of our product, and now we have a balanced equation. So from here we are going to look at the oxidation numbers. Sulfur trioxide will have exactly the same oxidation numbers as they had with the previous calculation, so we're just going to carry those oxidation numbers over. It has a +6 oxidation number, oxygen always -2. Oxygen over here always -2. Over there we have oxygen again, which is always -2. Hydrogen will always be +1. as long as it is part of a compound. Remember, when oxygen or hydrogen or any of your other gases that form diatomic molecules are bonded to itself, so H2, N2, O2, Cl2, they have an oxidation number of 0. But the moment they form part of a compound that contains other elements, then they will start using their oxidation numbers as we've assigned it to them. If we quickly go and work out over here, remember that the sum of the oxidation numbers, we've got 4 oxygens over here, should add up to 0. And for the hydrogen, we've got 2 over there. So we need to go and find the sulfur that would be in here if I had to add it in. 4 times -2 is -8. 2 times +1 is +2. So plus 2 plus how many ever my oxidation number for sulfur would be, plus the -8 that I have for oxygen must add up to give me 0. And we see that the oxidation number for sulfur then works out to be +6. If I go and I quickly calculate my oxidation numbers over here, again I would notice that my hydrogen is +1. And if I go and I add the oxidation numbers together so that they give me 0, I have 7 oxygens, so it is 7 times -2, and I've got 2 hydrogens, so it's 2 times or twice the negative or the +1 over there. You will find that if I work all of that out, that my sulfur again works out to have an oxidation number of +6. You would notice that the 2 over here that I used for the balancing does not influence my calculation at all. So if I look at it, I notice that my sulfur remains +6 throughout the entire reaction. So there is no loss or gain of electrons. My oxygen remains -2 throughout the reaction. So there is no loss or gain of electrons. And then lastly, I notice that my hydrogen over here also remains +1. There's the one behind there, throughout the reaction. So there is no transfer of electrons that takes place. If there is no transfer of electrons taking place, then this is not a redox reaction. Then I simply go and write over here next to my equation, or as my answer, that it is not a redox reaction. And obviously, if it is not a reaction, I won't have a reducing agent or an oxidizing agent. Let's see what question 3 asks us. Question 3 asks us to identify whether the following reactions will occur. Now remember, we had a quick look at that in the previous question, whereby we looked at a change in oxidation numbers to determine whether it is going to be an oxidation-reduction reaction. Also be very careful when you do this that you are able to refer back to your standard reduction potential chart. We don't have the full chart over here, so I'm just going to give you a brief example of what you can expect. If I have a spontaneous reaction and I find the reactants on, or the half reactions on my chart, and I read my reaction, the top reaction from the right-hand side to the left-hand side, and the bottom reaction from the left-hand side to the right-hand side, and I circle the element or the ion that I start off with, you will notice that if I connect these, it would give me a positive gradient. Now, if I see such a positive gradient on my standard reduction potential chart, then I know that the reaction taking place between those two chemicals would be a spontaneous reaction. As a joke in class, I always tell the children, seeing that my first name starts with a Z for Zelda, I tell them if they find the Z over there, they must remember their science teacher is spontaneous when it comes to teaching them, and therefore the reaction is going to be spontaneous if they see that Z that they form on their reduction chart. That is why I tell them as well, make sure you've got pencils, colors, highlighters, so that you can go and underline and circle information on that standard potential chart. So if you see that positive gradient connecting the two reactants, then you know it's a spontaneous reaction. If it was a negative gradient going from that side over to your right-hand side at the bottom, then it's going to give you a negative gradient, and that is a non-spontaneous reaction. And if you have a non-spontaneous reaction on your chart, then you know that would not be a reaction that will take place. So over here with this specific one, although we don't have the chart for you to prove it, we know that the reaction between iron and magnesium sulfate is going to be a non-spontaneous reaction, and therefore no reaction will take place. All right, so let's look at question 3.2. There they tell us that we start off with aluminium and it reacts with zinc sulfate. Now, if you go and you look at the two reactions over there, they would appear on your chart as such. Your oxidation half reaction would be that of aluminium, because we start over here with the aluminium, and that aluminium is going to lose electrons and carry a 3+ charge, and there will be 3 electrons over here. Your reduction half reaction over here would be the one where zinc goes and gains the electrons. So your zinc would gain electrons and turn into zinc metal, which has got a 0 oxidation number over there. So now that we've got our oxidation half reaction and our reduction half reaction, we will see that we started off with aluminium, and if that was on your reduction potential chart, your aluminium would have been at the top on the right-hand side, and your zinc would have been at the bottom on the left-hand side, giving us a spontaneous or a positive gradient over there, telling us that we have a spontaneous reaction. And therefore we know that over here a reaction does take place. Question 3.2. Again, now they give us magnesium and zinc sulfate. This one is very easy. We had it earlier on as one of our examples, and over there we could see that it is a spontaneous reaction. So without stressing too much about using our reduction potential chart, we go back to the information that we remember from previously, and we know that if I go and I look at my table, that I have magnesium that I'm going to read in this direction, and I'm going to have my zinc ions and I'm going to read it in this direction. It gives me a positive gradient on my chart. So over here I have a redox reaction that is taking place. And I hope you can still remember our half reactions over there. We start off with magnesium. Magnesium is going to be my oxidation half reaction, because it is going to lose electrons and turn into magnesium 2+. And over here, for my reduction half reaction, I'm going to have my zinc, which is going to gain 2 electrons, and it is going to form zinc metal. Last question over here, question 3.4. I have magnesium and iron nitrate. Now you will quickly over here notice the brackets over there. That is because iron has 2 bonding arms with which it can react, and the nitrate only has 1. So each iron atom can accommodate 2 nitrates, and that is why we put the nitrates in the bracket with the 2 on the outside of the bracket. So if we were to go and look over here, your oxidation half reaction would be that of the magnesium. So if it was on my table, I would start off with my magnesium on this side, read it from right to left, and over here I would have my iron. That 2 at the bottom tells me that it's going to be a +2, and I'm going to read it in this direction. So connect the 2 reactants with each other, it gives me a positive gradient, and it's going to be my reduction half reaction. So I'm going to start off with magnesium, which is going to lose electrons, become magnesium 2+ with the 2 electrons that it has lost, and my iron is going to gain the 2 electrons, and it is going to become Fe, or iron atoms over there. So that is this very quickly over there, question 3. Question 4 asks us, or gives us a nice example, which is a practical one that we look at. They tell us that we have copper that reacts with silver nitrate. Now, if your teacher has ever done this experiment in class, you'll know it gives a beautiful result. You start off with silver nitrate, which is a colorless solution. And if you then put a piece of copper in there, very quickly you will notice that silver crystals starts forming on the piece of copper that you inserted into the solution. If you leave it in there long enough, it will start looking like a tree that is covered in snow. This is why this experiment is very often referred to as the silver tree experiment. If you leave the reaction to take place long enough, the amount of silver that sits around the copper will grow and it will become all soft and fluffy, with the silver being very visible as a silvery shiny metal over there. You will also notice that the colorless solution goes from colorless to blue. Now, this blue color that you notice in the solution is because of the copper ions that are being released into the solution. So what we notice is that the copper will lose atoms as the electrons are lost, and it will form copper ions inside my solution. So it will go from copper metal into copper ions. In the meantime, my silver, which was in a solution over here, which means it is an ion, will gain the electrons. And when it gains the electrons, it will form solid silver atom particles over here that will accumulate around my container. And that is then the silver deposit that forms over there. So there is immediately, just by looking at the diagram, we can see that the one loses electrons that are released over here, and the other one gains the electrons. So they ask us over here to write the half reactions. Remember, loss of electrons is going to be your oxidation half reaction. So your oxidation half reaction, which one loses the electrons? Well, the copper goes from being neutral. Over there, let's quickly look. Your copper changes into copper ions. So there is a loss of electrons. So we start off with copper, and that copper is going to lose electrons to turn into the copper 2+ ion that we have over there. Your reduction half reaction over here would represent the silver that is then going to gain the electrons. So the silver ion takes in the electron to form silver metal. Now over here, just very quickly, I have a suspicion they'll ask us for a net reaction just now. I just want you to notice that the number of electrons are different. Remember what I said a lot earlier? If you have different number of electrons, you're going to balance your half reactions. So let's see if question 4.2 actually does ask us for the overall net reaction. They asked us over here for the half reactions, which we've done. We've given the 2 half reactions. 4.2 asks us to identify the oxidizing and reducing agent. Let's just go back to 4.1. I actually want to show you all this. If we go and we look for a net equation, remember, in a net equation, we need to cancel the electrons. So I have 1 electron over here, but 2 electrons on that side. So to balance it out, I need to multiply everything over here by 2. That will give me 2 silver ions and 2 electrons and 2 silver atoms on that side. Now that I have balanced my electrons so that I have 2 electrons and 2 electrons, now I can go and work out a net equation. My electrons will cancel out, and if I add the left-hand side together, I will see that I have copper and I have 2 silver ions on my reactant side. They will form copper ions on my right-hand side, and I will have 2 silver atoms that form for each copper ion that loses its electron. All right, so now we've done over here your oxidation half reaction, your reduction half reaction, and as a bonus, we've also looked at the net reaction, just so that you guys are familiar with balancing the equation over there. 4.2 asks us to identify the oxidizing and the reducing agents. Remember, if it undergoes oxidation, it is going to be my reducing agent. So the one that underwent my oxidation over here would be my reducing agent. So my reducing agent in this case is going to be my copper. We're not working with iron. So oxidation half reaction was my copper, And if it undergoes oxidation, it's going to be my reducing agent. So over here, it is going to be my copper. I seem to want to write the Latin name of cuprum over here for copper. All right, so your copper is going to be your reducing agent, and if that is my reducing agent, automatically my oxidizing agent is going to be the silver. All right, 2 easy marks for question 4.2. Question 4.3 tells us that we now work with a chlorine solution, or chlorine that is added to a sodium bromide solution. We're going to start anew by looking at the total chemical reaction. So they tell us that we have chlorine and that it is added to a solution of sodium bromide. They want us to give the half reactions for this specific reaction that takes place. So if we go and we look at the chemical equation, we'll see that we have sodium bromide, and this is going to react with the chlorine, and this is chlorine gas as a diatomic molecule that is added into the solution. When this reaction takes place, sodium chloride will form, and we're going to have bromine gas that is liberated or given off. If you go and you look over here, you will notice that you need to do some balancing, and I need to do some checking because it's not Cl2, it's just a Cl. And if you go and you look at that, then you bring in the 2 by balancing it in front over there. So that is the overall chemical equation. Now they want us to look at the half reactions, and those half reactions are then for your oxidation and your reduction half reactions. Just to quickly help us determine which one is oxidation and which one reduction, if you go and you look over here, your chlorine gas originally had a 0 oxidation number. Now chlorine and bromine are both group 7 elements. All your halogens, which we find in group 7, have oxidation numbers of -1. Knowing that information, we can go and look over here and see that chlorine, if it is a diatomic or unbonded, it's going to have a 0 oxidation number, but the moment it is bonded and forms part of a compound, then your chlorine will have a -1 oxidation number. Your bromine over here is part of a chemical bond, so therefore it will have a -1 oxidation number, and over here it is a diatomic gas and its oxidation number will be 0. So it has gone from -1 to 0, which means that electrons were lost. So the loss of electrons is an oxidized reaction, and over here I had your chlorine go from 0 to -1, so there was a gaining of electrons, which means that that was my reduction reaction. So when they ask me over here to give the half reactions, we can quickly go and do that, and we say that our oxidation half reaction is the one where the loss of electrons occurred. So we started off with bromine, and our bromine then lost the electrons to turn into your bromine gas. So it went from bromide into bromine, and we see that over here we start off with the bromine ion, and it is going to turn into your bromine gas, and there are 2 electrons over there that is liberated over there. So the loss of electrons occur over there. You see the 2 over here, so we need to bring it in, and that also balances the electrons on that side. And if we then go and we look at our reduction half reaction, for your reduction reaction, we started off with the chlorine. The chlorine gas then went and gained an electron and turned into your chlorine ion. Now you'll see that you have the 2 over there. We balance it by bringing in the 2 in front, and we write the 2 electrons on that side. So we have over here our oxidation and our reduction half reactions. A little bit more tricky if you only work with the equation over there, but remember, when you do this in the exam and when you work with this in class, you're going to have your standard reduction potential chart with you, and it's going to make it a lot easier for you to work with it then, because you're going to be referring back to the chart all the time. Question 4.4 asks us to give the balanced net equation for this reaction. Now we've done the oxidation and the reduction half reactions. I'm just going to quickly rewrite those again so that we can go and determine our net reaction from there. You'll remember that your oxidation half reaction was the one where your bromine gained or lost the electrons, and turned into your bromine gas. And we would have the electrons over here, so we balance it by bringing in the 2. and we have a reduction half reaction, and that would be the one where the chlorine gas, which is the 2, gained the electrons and turned into your chlorine ion on this side. So we balance that equation. So that is where we were for question 4.3. Now question 4.4 asks us to do the net equation, and to do the net equation we need to cancel out the electrons. I like doing that in a different color so that I can see what I'm cancelling out. So there my electrons will cancel, and I can just go and add the left-hand side for my reactants and add the right-hand side of my arrow. So over here on my left-hand side, I'm going to have my chlorine gas, and that is going to react with the bromine. Remember to bring in the 2 over there, your 2 bromide ions over there, and it's going to form your bromine gas, Br2, and the chlorine ions, Cl minus over there, 2 molecules of that. And there we have a balanced equation. You will see that the balancing already occurred when we started balancing out the electrons. So that comes through over here. Question 4.5, last question. They want us to identify the spectator ion. Spectator ion is the one that didn't take part in any of this. The oxidation number remained the same. And if you go back to the original equation that we had over there for 4.3 that I wrote down for you, if you look over here, the only change that occurred was between chlorine and bromine. Your sodium over here just stood there and observed the reaction taking place around it. So if we go and we look at the answer for 4.5, your spectator ion in this case is going to be the sodium. Also, if you just write there the Na+1 ion, that would be accepted as your answer. I don't know about you, but I'm now happy to be stepping off the whole section of redox reactions because it's so many numbers going around. Question 5 and question 6 is dealing with acids and bases. So let's move on to those 2 questions to wrap up this section. Question 5 tells us that hydrochloric acid is a strong acid. What does this mean? Now, by definition, we know that an acid is a proton donor. So if it wants to donate the proton, it needs to break up into the ions that make up that specific compound. And one of those ions will be the hydrogen ion, which carries the proton. Now, that process whereby it breaks up, the compound breaks up into the ions, is called dissociation. So the word dissociation is going to come into our answer over here because they want to know what makes a strong acid. What does it mean when someone tells you you've got a strong acid? Strong acids are characterized that they dissociate completely in water to release their hydrogen ions or to liberate the hydrogen ion over there. So your answer over here would be that a strong acid or strong acids will dissociate completely when mixed with water or when dissolved. All right, that basically means that hydrogens or hydrogen ions are released easily. Okay, 2 marks, straightforward definition over there, definition for a strong acid. Question 5.2. They tell us that 20 grams of calcium carbonate reacts with an excess of dilute sulfuric acid. Now remember, when we deal with an acid-base reaction, the one has to be an acid and the other one is going to be a base. All your carbonates, if they end off with the CO3 ion over there, all right, if you can identify that carbonate over there, you know that that is a base that you are working with. So over here, they tell us that we've got calcium carbonate and it reacts with sulfuric acid. Remember, grade 11s, you must know your acid formulas. Your basic acids that we work with, sulfuric acid, hydrochloric acid, nitric acid, those are formulas that you must know, and you should be able to use them in equations over here. So they ask us to provide a balanced equation for the reaction. Now there's a simple rule that I want you all to remember, and I'm going to put it in a different color because it's not part of your answer. When I have a carbonate, any carbonate that reacts with any type of acid, it will always form carbon dioxide gas, it will form water, and it is going to form a salt. Now this salt will depend on whatever compound I had and also the type of acid that I had. Now they told us over here that we started off with calcium carbonate. Calcium carbonate is CaCO3, and it reacted with the acid over here, which was sulfuric acid, which is H2SO4. Now, if it is going to form my carbon dioxide and my water, I know this, so I write those down first. Now to go and figure out what the salt is. So let's just eliminate from here everything that we already have as a product. I've already used my hydrogen, and I've already used all of my carbon and my oxygen over here to make the carbon dioxide and the water. So you will now see that you basically have your calcium ion and your sulfate ion left. Calcium, being a metal, forms a +2 valence charge, and your sulfate has got a -2 valence charge over there. So if those two combine, they're going to form substance called calcium sulfate, CaSO4. So now that you've eliminated the hydrogens and the carbon and the oxygen to form those two products first, it is easy to just go and put the two that are left over, the two ions, put them together, and that is going to give you your compound that you have over there. And there we have our reaction. Now the big job is just to go and make sure that everything is balanced. You have two hydrogens on your product side, one sulfur, 4 oxygens, part of your sulfate. Over here you've got 2 oxygens and 1 oxygen, which is going to give you the 3 that you had with your carbonate. You have 1 carbon and 1 calcium. So that is going to be your overall balanced equation already. No balancing required. As you write it, that's the way it's going to be. Let's look at the next question. Question 6, the last question for this section. And this is a nice practical application, something that we deal with in our everyday life. They tell us that the stomach secretes gastric juices. Now, in your stomach, all of those juices also contain, amongst other things, hydrochloric acid. Hydrochloric acid is one of our very strong acids that we deal with in the lab. And they tell us that these gastric juices help with digestion. Now, sometimes there is an overproduction of acid, and that leads to heartburn and indigestion. Antacids, those are things like Enos and Gaviscon that you guys drink to release the heartburn, can be taken to neutralize the excess acid. Another substance that we use as an antacid is milk of magnesia. Now, milk of magnesia is only slightly soluble in water, and it has a formula of magnesium hydroxide, which is Mg(OH)2. They want us to go and write a balanced chemical equation to show the antacid as it reacts with the stomach acid. Again, I'm going to give you a rule that will help you to determine the correct chemical formula over here. And again, I'm going to write the rule for you in a different color, just so that you remember not to write that as part of your answer, because they're only asking you for the chemical equation. So the rule over here tells us if I have a hydroxide, any type of hydroxide, and I allow this hydroxide to react with an acid, it will always form water as a product. So H2O will always be formed, and it will then form a salt. Now, just like with the previous equation, the type of salt that is formed will depend on the chemicals that you use in the reaction. In this case, they told us that we had magnesium hydroxide, Mg(OH)2, and they told it was going to react with the acid in your stomach, which is hydrochloric acid, HCl. Now, if it will always form water, you write down the water first. So water is one of your products that always form, and then just go and identify those elements that will form water, and look what you are left over with. You are left over with magnesium, you are left over with chlorine. So those two compound elements will form a compound, and that compound will be the salt that you have over here. So if we go and we look at that, your magnesium will always form a +2 ion, chlorine a -1 ion, and if they combine to form the ionic compound of magnesium chloride, it will form magnesium chloride and a footnote 2 over there, because the +2 is going to transfer, and you're going to need 2 chlorines over there to react with that. Okay, so that is now our reaction. But they asked us for a balanced reaction, so now we need to go and double check quickly that our reaction is balanced. You will see that you have 2 hydrogens over here on your product side, as well as 2 chlorines. But on your reactant side, you only have 1 molecule of hydrochloric acid, which is 1 hydrogen and 1 chlorine. So you're going to bring in the 2 over here to balance it. And you will see that you've got 1 magnesium, 1 magnesium. The 2 over here means that you've got 2 hydrogens. It means that you've got 2 oxygens. So if I add those 2 hydrogens to the 2 hydrogens that I have there already, it means that I'm going to need 4, so I bring in additional 2 over there. So just to highlight the balancing so that you guys can see it, I've added the 2 in over there, and I've added a 2 in over there. My magnesium is balanced as it is, so I don't need to bring in any further balancing. So that was 6.1, where they asked for a balanced chemical equation. They now go and they ask us, or they tell us that the directions on the bottle recommends that children under the age of 12 only take 1 teaspoon of milk of magnesia, but adults can take 2 teaspoons. They want us to briefly explain why these dosages are different. Well, if you go and you look at the body of an adult and you compare that to a child, you would notice that firstly, the stomach is slightly bigger. Also, as an adult, your stomach is going to produce more stomach juices or stomach acid over there compared to that of a child. So because the production of hydrochloric acid is higher, the adult would have to use more milk of magnesia to neutralize any excess acids. So when we go and we formulate our answer, we need to keep those 2 pieces of information as part of our primary answer, that an adult will produce more hydrochloric acid and therefore would need to consume more milk of magnesia to neutralize it. So let's just formulate our answer over there. You would state over here that adults produce more gastric acid or gastric fluids, and by gastric fluids I'm referring to stomach acid. Than young children. Let's just correct the spelling over there. My English teacher would run away if she saw that. All right, then young children. Therefore, they need to consume more milk of magnesia. And why do they consume that? They need to consume the milk of magnesia to neutralize excess acid. Okay, let's look at question 6.3. 6.3 asks us, why is it not recommended to take an overdose of antacid or stuff that will relieve heartburn over there? They want us to refer to the hydrochloric acid concentration in the stomach. Now, when you consume milk of magnesia or any type of antacid, what it basically does is it allows an acid-base reaction to take place. This acid-base reaction causes the base to neutralize the effects of the acid. That is going to increase the overall pH in your stomach. But as it increases the pH, you would remember from the balanced equation that we have over there, that as it reacts with the hydrochloric acid, it reduces the hydrochloric acid in the stomach. And if the hydrochloric acid is reduced and there's not enough hydrochloric acid, you're going to suffer from indigestion, in the sense that your stomach won't be able to digest your food anymore because there's not enough acid to assist in the digestion of your food over there. So when you formulate your answer over here, you would have to refer to the concentration of the hydrochloric acid, or the HCl, that reduces to such an extent that it can't help with the digestion of the food in your stomach anymore. So we'll formulate our answer. When too much antacid is consumed, it neutralizes, let's just correct that, neutralizes the hydrochloric acid This reduces the concentration of HCl, which is your hydrochloric acid, in the stomach. If there is an insufficient concentration of HCl, proper digestion cannot take place. Okay, so there we've got the answer over there. Remember, two types of reactions that we deal with when we've got reactions in grade 12. We deal with acid-base reactions, and there we have a transfer of protons that occur. It is your hydrogen that moves around. And the other type of reaction is your redox reaction. With the redox reaction, it is electrons that move around between atoms and ions, and it is a direct transfer or an indirect transfer. When you have a direct transfer, that is a spontaneous reaction, and an indirect transfer is going to be a non-spontaneous reaction, and you need electricity to get that reaction going. Also remember that when you work with your standard reduction potential chart over there, that you need to make sure of the chart that you are going to use. Different teachers will teach you to use different charts. Some schools refer to the chart labeled 4A, and some schools will use chart 4B. Remember that the notes as they were set out over here for you guys, for this section we used chart 4B, which starts with lithium at the top and ends with fluorine at the bottom. Make sure that you use the correct chart, because if you apply the incorrect chart over here to solve your problems, you're not going to get the answers as the marker or examiner would expect you to get them. I wish you guys the best of luck for the end of year exams. I'm sure that types of reactions are going to be easy peasy for you as from now on, and I look forward to working with you guys again. Thank you very much.